Hey everyone, I wanted to make you a screencast to talk about how we deal with weak acids. We've already covered in class how you deal with strong acids and finding pH values for aqueous solutions of strong acids. I want to talk you through the process of how we deal with that when we're dealing with a weak acid. So some things to remember just as review. When we're talking about an acid, remember that our Bronsted-Lowry definition of an acid is anything that donates a proton. It's a proton donor. And when the acid does that, it forms two things. Obviously, it donates the proton, and it also forms something called a conjugate base. Now, we talked about identification of conjugate acids and conjugate bases at the beginning of our POGIL activity that we worked together with in small groups. Another key piece of information that we need to consider when we're dealing with acids or bases are the possibility of an equilibrium process dominating the chemistry of what's going on. And for weak acids, equilibrium is definitely in play. We have weak acids are things that don't tend to ionize, which means that we have to recall how we write laws of mass action. And so you notice here, this is the law of mass action for the equation shown above. Now, let's talk for a moment about what makes an acid strong and what makes an acid weak. Strong acids are things that fully dissociate. So if you notice here, we've got a certain concentration of an acid, HA, and it breaks apart in water completely, 100%. So if you have 100 molecules of HA, they will dissociate into equivalent numbers of hydrogen ions and conjugate base particles. That's for a strong acid. Now, what we're focusing on in this screencast are not strong acids, but rather weak acids. And weak acids are different. When weak acids reach equilibrium, they have only partially dissociated. That means they don't form as much hydrogen ion in solution given equivalent molarities. So the pH we would expect to not be the same at all, even if we had equal concentrations of a strong acid and a weak acid, their pH values would be different because they don't produce the same amount of H plus in solution at equilibrium. So let me show you how we deal with that mathematically, because conceptually I think we can see that in these bar graphs, but mathematically it takes a little bit of organization to make sense of things. So we're going to start with a simple problem dealing with a very common weak acid, acetic acid. You might know this as vinegar. Notice I give you the formula here. And notice I also give you the equilibrium dissociation constant, Ka, 1.8 times 10 to the minus fifth. You can identify a weak acid purely by the value of Ka. When Ka is smaller than 1, you're dealing with a weak acid. Now, the first step whenever you're doing a problem like this, always start by writing the dissociation equation. You need to be able to think through how the acid actually breaks up into ions in aqueous solution. So for acetic acid, it's a monoprotic acid, meaning it only has one hydrogen that's ionizable. So it will produce a proton, a hydrogen ion, when it dissociates, and it will also produce a conjugate base. The conjugate base is the acetate ion. All of these three species are aqueous. At this point, it's also good to practice writing the law of mass action. And the law of mass action for this process, the equilibrium expression, would be concentration of H plus multiplied by the concentration of the conjugate base, C2H3O2, negative 1, divided by the concentration of the undissociated acetic acid. So these are two things that you should write out before you go any further with the problem. So you've done that. Let's think about what's next. The next piece is to use a technique that we used in Unit 8, which is to think about our initial conditions, how things will change, and what our equilibrium positions will be. So that means making an ice table. So you notice I've already got our dissociation equation listed, shown here. And now what I'm going to do is read the problem carefully and pick out information that tells me initial amounts. So this initial concentration that's provided here, that's going to be my initial concentration I'm going to list in the table, 0.50 molar. Now, under initial conditions, I assume the acid hasn't had the opportunity to dissociate yet, which means there's no conjugate base and there are no hydrogen ions in solution just yet. Now what we know is that Ka tells us that even though we would not expect the acid to dissociate very much, there will still be some of the particles that will form, some of these cations and anions that will form through dissociation. So if you imagine if you had 100 molecules of this acid, maybe 2 or 3 of them will break apart. Now we don't really know if it's 2 or 3 or 20 or 30, so we use a variable here to describe the change. So we do know that some will form. That's a positive value because originally it was 0. And it's going to be plus x for both ions. That's because there's a coefficient of 1 in front of each. We keep these values stoichiometrically proportional. And so if those values are positive, in terms of the acid, it's going to decrease by some amount, x. All of our mole ratios are 1 to 1, so we don't have to worry about adding coefficients or anything like that in our change row. And to find our equilibrium, we just combine those values like so. So now we've completed our ice table. And let's just think about what we're going to do next. The next piece really only focuses on the equilibrium amount. I mean, really, this is the whole point of understanding how the acid behaves, is thinking about how it is going, what the situation will be at equilibrium. So we're going to take just those values. And so here I've transcribed all of the equilibrium amounts for all 3 species that we could have in solution. And now we're going to go back to that equilibrium expression that we wrote previously. Now instead of putting Ka here, I'm going to actually write the numerical value for Ka that was given. And it was 1.8 times 10 to the minus 5th. And I'm just going to plug in the rest of my values from my ice table into my law of mass action. Now at this point, traditionally what we would do when we were studying equilibrium for the first time is we would just go through and solve using quadratics and find a value for x that was reasonable. There is a simplification that we can make here. For this particular acid, it's weak. It's quite weak. And this is an assumption we can make with all of the weak acids and all of the weak bases that we'll come in contact with in this course. The assumption that we make is this amount of acid that actually breaks apart is small. So small that we can make an assumption. And the assumption here, I'll write it in purple. The assumption that we can make is this expression is essentially the same as if we ignored this contribution of x actually dissociating. So what that means is x is going to be so small that it won't really change the value of the 0.50 molar solution substantially, where it will actually impact our calculated result. So it might be helpful now to kind of write out the entire expression here in red to show how we would solve that. So when you're dealing with a weak acid, we can make an assumption. Remember, that assumption is that this amount is small in comparison to the molarity of the solution, therefore we can ignore it. And we use that to make solving the problem a little bit simpler. So now we have our problem here in red to solve, and we can use algebra to solve it. And when you do that, you'll get an x value of 3 times 10 to the minus third. Now remember what x means. X is our concentration of conjugate base, and it's also our concentration of H+. That means we're going to use this number value to find our pH. So once you've found your value for x, you can plug that into our expression for finding pH. pH is the negative log base 10 of the hydrogen ion concentration, which happens to be 3 times 10 to the minus third. And you can try that on your calculator and see what number you'll get. And you'll notice that it's quite a different number, quite higher than if you were to just take the negative log base 10 of the acid concentration. So that's the process, and this process works the same whether you're dealing with a weak acid or a weak base. You're going to have to use ice tables and concepts of equilibrium. Have a great day. We'll see you in class.